So now we're going to move on to surds. So before I talk about surd equations, I just want to go over surds in general. If you just want to look straight away at the surd equations, feel free to skip over. Make sure that you are happy with surds. I suppose surd equations can be asked, and other types of questions on surds can be asked. And I suppose some of them mightn't feel relevant here, but I just would like to cover all of the surds together. So surd is just another name for a number which can be written as square roots. Basically what I'm talking about is root 2, root 3 and root 5. So root 4 wouldn't technically be a surd because root 4 simplifies to 2. So any number which is written with a square root, we often call that square root the surd. So we call these surd numbers. So you remember that these numbers are irrational, so hopefully you remember that. So they're infinite non-recurring decimals, so this means they go on forever after the decimal point and they don't repeat themselves. So any decimal version you write down will have rounding. So using this surd form is the most accurate way of writing the number. So for example, if you have your calculator in front of you and you want to do root 2, most new calculators now, if you type in root 2 equals, you'll get back root 2 and you'll have to use the change button or the SD button depending on which calculator you're using to figure out what it is as a decimal. So square root of 2 gives me, and I'll actually just write it in here so you have it. So square root of 2 equals 1.4142135562, and that's where my calculator stops because that's where I've set it to stop. Some people's calculator might do less, some people might do more, but that has been rounded. You might look at it and say, well, really? But actually it has. So if you take that number and you square it again, so type into your calculator 1.4142135562 and square it, you actually get 1.99999. So actually we've made it inaccurate, we've rounded it. So using the surd form is much more accurate than putting it into decimal. I know people don't like the surd form, it's similar to the fractions, but it is the most accurate way. So looking at the properties of surds now, so there are really three that you need to know and you need to be able to work with. And that is, if you have the square root of AB, which means A multiplied by B, you can separate that out. It's like the square root of A multiplied by the square root of B. So if you think of it like this, I have A multiplied by B. That's the same as the square root of A multiplied by the square root of B. So I suppose you could look at this as the multiply can happen underneath the square root or outside the square root. So the second property you need to work with is quite similar. It's about a fraction. So if I have a fraction, and remember with fraction we have division. So really what this is, if I have A divided by B under the square root, it's the same thing as A, the square root of A divided by the square root of B. So remember that fraction means division. So those two are like the opposites of each other. Okay? And then the last property that we have is the square root of A by the square root of A is the square root of A squared, and that equals A. Okay, so basically the square root of A is equal to the square root of A is equal to the square root of A squared, and basically what happens is the A squared and the root, they cancel, so I'm just left with A. Okay, so we can work both ways with that. It's like the square root squared, or you can use it like we had in the first property, that actually you're working backwards, you're putting them back under the same square root. Both will lead us back to A. So it's also important that you're familiar with the perfect squares. So we would have talked about this when we did our factorization, specifically the difference of two squares. It's also quite important to know when you're talking about squares, we will talk about completing the square in different areas, but what we're talking about then with squares are these numbers here. So 1 is a perfect square, 4, 9, 16. So perfect square is a number whose square root is a whole number. So for example, 16 is a perfect square since the square root of 16 is 4. So I would definitely make sure that you know all the way up to 169. So we have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and 13 squared. And I do know that you may not have come across 13, but they do love to throw this in, especially with the difference of two squares. 169 is 13 squared. Okay, you can always check on your calculator if it is a perfect square, if it's a much bigger number, or if it's one of those numbers and you just don't recognize it. You can use your square root button. Okay, so for example, if I gave you the number 196 and I said, is that a perfect square? Well, what you would do is put into your calculator square root of 196. So if you have your calculator in front of you, try it now, and you should get 14. So you'd say, yes, it is a perfect square. If I gave you the square root of if I gave you the number 200 and asked, is that a perfect square? Same method, we do the square root. So if you can do that now, put it into your calculator, and what you'll find is you will be left with a third in the first instance if you're using a new calculator, and what the new calculator will give you is 10 root 2, and if you convert it, it gives you 14.14 on. And basically what that means is it is not a perfect square. So that one is not a perfect square, that one is a perfect square. So just get used to using your square root buttons to help you out in case you don't recognize a number. So let's look at using these properties of surds. Okay, so simplify each of the following. So the method that we use to simplify surds is we're going to try and see, is there a perfect square that will divide into the number? So think of your perfect squares. Okay, we have 1, 4, 9, 16, 25, and so on. Looking at that first one, hopefully everyone will see that 99 can be written as 9 times 11. Okay, and using the first property of surds, we can write that as the square root of 9, square root of 11, and we can simplify the square root of 9 to 3 root 11, and that's your answer. So always the same method. Is there a perfect square that we can divide in? So let's work for the moment just with this bit here. Let's not forget it. I'm going to highlight it because often we can forget it. So I don't want to forget it, and actually it might be easier for us to keep it as we work through our surds so we don't forget it. So square root of 112. So what is the biggest perfect square that can go into it? So we could say 4 goes into it. Does anything else go into it? Well, 16 goes into it, and you can check that. So basically I can separate this into 16 times 7. So what you could do is you'd say, well, the first perfect square is 1. That's not going to be of any help. The next one is 4. So 112 divided by 4. But that gives me 28. And when you see the number 28, hopefully you know that 4 also divides into that. So you'd say, well, actually 4 isn't the biggest perfect square that goes into it. So we're going to get a half of the square root of 16 by the square root of 7. Which gives me a half of 4 root 7, and a half of 4 is going to give me 2 root 7, and that's my answer. Okay, so now we have 2 1/4 under our square root. So in maths, we very rarely use these type of mixed fraction where there's a whole number and a fraction. More likely we are going to use either an improper fraction, okay, or a decimal, okay, so depending on the question. We're going to use an improper fraction or a top-heavy fraction. So hopefully you remember how to do these. The method is 4 by 2 is 8 plus 1, so it gives me 9 over 4. So this is a real flashback to primary school. Hopefully you remember that. Okay, so if you remember our second property of surds, we could rewrite this as root 9 all over root 4, which gives me the square root of 9 is 3 and the square root of 4 is 2. Okay, so these aren't overly complicated, but they do require some practice, like everything, because it's very easy to look and say, oh yeah, that's simple. But sitting in an exam, if you haven't seen them in a while, you might panic and say, I can't remember how to do this. So we're always just trying to find the biggest perfect square that we can divide in. So let's look at example 6. So here we're going to just put a few different simplifications, or a few different of the simplifying together, and then we're going to add and subtract. So express the following as a surd in its simplest form. So this should be one surd. So there's very little I can do with it at the moment. So what I want to find is, I want to find what perfect square will divide into 180. Okay, so I could divide 180 by 9 and I get 20. And 20 is divisible by 4, so it's not the biggest. So you can go up, and hopefully what you'll find, through a little bit of trial and error if you need to, is that this is 36 by 5. Okay, 20, hopefully you can see very quickly, is 4 by 5 minus, and this is 25 by 5. So what I'd like to point out at this point is we have a perfect square of 36 and a 5, the perfect square of 4 and a 5, and the perfect square of 25 and a 5. So if you were able to find, or able to simplify one of them, and I suppose the one that I would lean towards is the root 20 because it's the simplest. It's the square root of 4 by 5. So the 4 is the perfect square. So if we were to simplify this, it would be the square root of 4 square root of 5, which will give you 2 root 5. Well, in order to add and subtract, all of those terms would need to have a root 5. So once you have this root 5, you could then really simply divide 5 into 180 and you'd get your 36, and 5 into 125 to get your 25. Okay, so you can do it either way. If you're happy to work with trial and error, or you can be clever about it, work out the simplest and say, well, if I'm going to have to add them, because they did ask for a surd, so they will add and subtract together, they're all going to have to have that square root of 5. So let's tidy up here. So what we have now is square root of 36 by square root of 5, and the square root of 36 is 6 root 5 plus, we still have our 2 root 5, and let's clean up the last term here. It's going to be the square root of 25 by the square root of 5, which is minus 5 root 5. So what I have here is 6 square roots of 5 plus 2 square roots of 5 minus 5 root 5. So I suppose if you think about this as a thing, so I have 6 of something, I add 2 of that something, and then I take 5 away. Okay, so even if we want to say apples, so I have 6 apples, I add 2 apples, so I have 8 apples, and I minus 5 apples, so I have 3 apples. Okay, and I think everyone will be well able to do that. But the square roots are worked in the exact same way. I have 6 of the square roots of 5. Then I add 2, so now I have 8 square roots of 5. And now I'm subtracting 5. So what I'm left with is 3 root 5. So they're added like they are things. Okay, so I have 6 of this thing, I'm adding 2 more, and then I take 5 away. So I'm left with 3 of those things. And I know it's kind of a hard concept to get your head around, but like I said, practice with the surds is really the only thing that will improve with this. It will help you improve your work. So now let's look at an example of a surd equation. So this is an equation which contains one surd. So we can see it there. We have x minus, and then we have the square root of 5x minus 1, and that equals 5. So the first thing we want to do with a question like this is to isolate the surd, or basically to get it on its own. So we want the surd on one side of the equals and everything else on the other. So let's go with that. So we get minus 5x minus 1 is equal to 5 minus x. So I just want to change all my signs so I don't have to work with the negative square root. So I'm going to have 5x minus 1 equals x minus 5. Now you notice that nothing changes under the square root. So what happens is this minus goes to a plus, this plus goes to a minus, and this minus goes to a plus. So then at this point, we have isolated our third, we have put it on its own on the left hand side, and now we want to get rid of it. So the way that we're going to get rid of it is by squaring it. So if you remember back to the third property we had when we were looking at thirds, it said that when we had the square root of a and we multiplied it by the square root of a, so effectively the square root of a squared, then we just ended up with a. So effectively what happens is the square root and the square, it's like they cancel each other. Okay, so what happens is we have the square root of 5x minus 1 and the square root of 5x minus 1, which will literally just leave 5x minus 1. So it just leaves me the bit that was under the square root. So x minus 5 all has to be squared out fully. You can do that by writing down the two brackets and doing that out fully. I'm just going to really quickly write it down as x squared minus 10x plus 25. So now, as you can see, we have a quadratic, so we want to get everything over one side of the equal. So we have a minus x squared plus 5x plus 10x minus 1 minus 25. I'll just clean this up, sorry, so you can actually read what I've written, and that equals 0. So just to clean it up a little bit more, minus x squared plus 15x minus 26 equals 0. And I'm just going to change the signs then. X squared minus 15x plus 26 equals 0. So that's the quadratic. So now we have to go and solve it. So I'm just going to write it back up here. Now, for solving it, the numbers are a little bit bigger. Guide number is absolutely fine to use. If you're not terribly comfortable using the guide number with the big numbers, then I would say go for minus b. Both will give the same answer. So you have plus 26. So we're going to have minus 2 by minus 13. So we have x squared minus 2x minus 13x plus 26 equals 0. X here is common, leaving me with x minus 2. Minus 13 is common here, leaving me with x minus 2. So what I have is x minus 13, x minus 2, which gives me x equals 13 and x equals 2. Minus b will, like I said, give the exact same answer. So we've got our two answers for x. However, for these third equations, it's so important that we check our answer. So this, you will lose marks if you don't do this. So you need to check. So the first one I'm going to check is x equals 13. So we have 13 minus the square root of 5 times 13 minus 1 equals 5. So let's clean this up. So we have 13 minus 65 minus 1 equals 5. 13 minus the square root of 64 equals 5. 13 minus 8 equals 5. And that answer is absolutely perfect. Okay. So now let's check x equals 2 and see does it work. So we have 2 minus square root of 5 by 2 minus 1 equals 5. So we get 2 minus 10 minus 1 equals 5. So we get 2 minus square root of 9 equals 5. So 2 minus 3 equals 5. Is that true? No, that's not true. Therefore, our answer is x equals 13. So this answer here does not work. So finally, let's look at the last example. So again, this is a third equation, but unlike our last example, which only contained one third, this example here contains two. So this does make our sum a little bit longer and a little bit more complicated, or rather the algebra in it becomes slightly more difficult, but all doable. So just like before, what we want to do is we want to isolate one of our surds. So it doesn't matter at this point which one you choose. I'm just going to keep my 5x plus 1 here on its own. So that equals 6 minus the square root of x plus 1. Okay, so just like before, I'm going to square both sides. And the purpose is to get rid of the square root. So on this side, we're left with 5x plus 1. However, when we get over to the right hand side, things are not as simple. So basically what we have is 6 minus root x plus 1 multiplied by 6 minus square root of x plus 1. So let's do out our long multiplication here. So basically we want to split our bracket, and then we have a minus root x plus 1 bracket 6 minus square root of x plus 1. Okay, so 6 by 6 is 36. The square root of x minus 1 by 6 is going to be minus 6 root x plus 1. Now we move over here. Minus the square root of x plus 1 multiplied by 6 will give me again minus 6 root x plus 1. Remember we saw earlier when we were looking at the properties of surds and those examples how we talked about it like a thing. So if that was an a, for example, it would be 6a. Okay, so here instead it's 6 by the square root. So now here we have, and I'm just going to do a little bit of an aside for this. So just up here where I might have a bit of space, I want to multiply the negative of root x plus 1 by the negative of root x plus 1. Well, what basically we have is minus the square root of x plus 1, all to be squared. So what happens when I square it is the square root disappears, but also it'll be a minus by a minus, so it gives a plus. So what I'm left with is just my x plus 1. Okay, so I have plus x plus 1. Okay, and the whole time I've had my 5x plus 1 here. 5x plus 1. So let's do a bit of cleanup. 36 minus 12 root x plus 1 plus x plus 1. So now you might notice that just like in our last example, we have a square root, one square root or one surd. So now I want to basically repeat the process. I want to get the surd on its own and everything else the other side equals, and then I'm going to square and then solve. So when there's two surds or there's two square roots that appear in the equation, we just basically have to run through our method twice rather than once. So let's see what that looks like for us. So we'll have the 12 square root of x plus 1. I've brought it across the equals. It was negative, it's now positive. Now I have an x and a minus 5x. I have a plus 36, a plus 1, and a minus 1. Okay, so I've just cleared the screen here just so we've more space to work. So we just need to clean up that right hand side. So we have 12 square root of x plus 1 equals minus 4x plus 36. So at this point you could be able to see that you can divide the whole way across by 4 to make our calculations easier. And if you don't see that, that's okay, you'll still get the same answer in the end if you don't divide across. So we end up with 3 root x plus 1 equals minus x plus 9. So now basically we're going to redo what we did at the start. So what we'll end up doing is we're going to square both sides of the equation now that I have that third term all on its own. So I end up with 9 because we have to square the 3 and then just what's underneath this square root.
and you can work this out the long way and that's absolutely fine, but what we'll end up with is x squared minus 18x plus 81. So now we just need to clean this up. 9x plus 9 equals x squared minus 18x plus 81. So when I clean that up, I end up with minus 27x plus 72 equals 0. Okay, so there's a few steps there, and work through them on your own, make sure you're happy with them. So let's solve this quadratic now. So no problem using guide number. If the numbers seem too big or you can't see the factors, then of course minus b is absolutely fine. So we're looking for the factors of plus 72. That adds to give me minus 27, and that actually works out as minus 3 minus 24. So so we get x squared minus 3x minus 24x plus 72 equals 0. X is common, x minus 3, and here minus 24 is common, and we're left with an x minus 3. So we get x minus 24, x minus 3 equals 0. So our two answers are x equals 24 and x equals 3. So now it's important that we go and we actually check these answers. So that's one really important part of the Surd equations, that we check both our answers to see are they both valid, or is there one that's valid and one that's not. So let's sub it in. 24 plus 1 plus square root of 5, square root of 24 plus 1, and that should all equal 6. So what I end up with is actually I have 11 plus 5 equals 6, and that is not true because that is not equal. So x equals 24 does not work. Okay, so let's try x equals 3. So square root of 5 by 3 plus 1, square root of 3 plus 1 equals 6. So 5 3s are 15 plus 1 is 16. Square root of that is 4, and 3 plus 1 is 4. Square root of that is 2, and that equals 6, and that is correct. So the correct solution to this Surd equation is just x equals 3.